Oh, welcome back to Fun with Physics with Jason and Will. I'm Lord Voldemort.
Problem 1087. A uniform rod of length L rests on a frictionless horizontal surface. The rod pivots about a fixed frictionless axis at one end. The rod is initially at rest. A bullet, traveling parallel to the horizontal surface and perpendicular to the rod with speed v, strikes the rod at its center and becomes embedded in it. The mass of the bullet is 1/4 the mass of the rod. Problem A. What is the final angular speed of the rod?
So for this problem, you have to use your before and after. So you look at the angular momentum before and the angular momentum after. Before is just the bullet. So you do m times velocity, which are the two given, times the lever arm. And that is going to be equal to the inertia times omega. So you have m times the velocity times the L over 2 because it strikes the rod halfway through. And that is equal to 4/3 times mass L squared omega. The equation for the rod is 1/3 ml squared, and the mass is 4m, so that's why the 4 is there. But you also need to add mass times 1/2 of the length squared times omega, because that is the addition of the bullet that becomes embedded in the rod after. So after you set up this equation, you use your algebra to get down the problem. So we took mvl over 2 equals 4/3 times the mass L squared omega plus ml squared omega over 4.
Done with the problem.
This problem then simplifies down to the mass times length squared omega times the quantity of 4/3 plus 1/4, which simplifies further to 6 times mass velocity length over 19 is equal to the mass length squared omega. Then you solve for omega by dividing by mass times length squared, and you get omega is equal to 6 times the velocity over 19.
Go.
Okay, welcome back to Fun with Physics with Jason and Tyler.
Hi, I'm Tyler. Part B. What is the ratio of the kinetic energy of the system after the collision to the kinetic energy of the bullet before the collision?
Alright, so here we have the equation for the kinetic energy before the collision. No, after the collision. Here we have the kinetic energy of the bullet before the collision. When you use the equations, it comes out to 1/2 times the quantity of 1/3 mass times length squared plus 1/16 mass times length squared times omega squared, which is 36v squared over 361 L squared. And that's all over 1/8 mv squared, because that's the kinetic energy of the bullet before. So you simplify that down to further in this step, and then again in this step, and then here you just cancel the mv squareds cancel here and here, and after dividing the numbers through you get 3/19.
Hi, welcome back to Fun with Physics with Jason and Will.
Problem 1061. The mechanism shown here is used to raise a crate of supplies from a ship's hold. The crate has a total mass of 50 kilograms. A rope is wrapped around the wooden cylinder that turns on a metal axle. The cylinder has a radius of 0.25 meters and a moment of inertia of 2.9 kilograms meters squared about the axle. The crate is suspended from the free end of the rope. One end of the axle pivots on frictionless bearings. A crank handle is attached to the other end. When the crank is turned, the end of the handle rotates about the axle in a vertical circle of 0.12 meters. The cylinder turns and the crate is raised. Question: what magnitude of the force F applied tangentially to the rotating crank is required to raise the crate with an acceleration of 0.8 meters per second squared? Hint: You may ignore the mass of the rope, as well as the moments of inertia of the axle and the crank.
First off, this problem is also not too difficult. So we separated out the two circles to make it easy to diagram. And what you first need to look at is the sum of the force to solve for tension, which is the tension of the rope that's attached to the circle. So we set up the equation, sum of the forces equal mass times acceleration. And the forces are tension minus the mass times the gravity of what it's lifting. So you get tension equals mass times the quantity of gravity plus acceleration. And when you plug in 9.8 for gravity, and you plug in 0.8, which is given for the acceleration, and you end up with tension equaling 530. So for the second part, you look at the sum of the torques, and you set that equal to the moment of inertia times alpha. And the two things you look at are on the larger circle with the tension, and then the force applied to the crank. So the larger circle is negative 530 times the radius of 0.25 meters, plus the force applied to the handle, which has a radius of 0.12 meters. And that's going to be equal to the moment of inertia times the acceleration over radius, which this simplifies out to negative 132.5 plus 0.12 times the force, and that's equal to 9.28. And further, 0.12 force is equal to 141.78. So when you solve for F, which is the force applied to the crank handle, which is needed to raise it with an acceleration of 0.8 meters per second, you get the force is equal to 1,181.5 newtons.
And checkmate. Well, thank you for joining us. Take it easy there, pal. Thank you for joining us with Fun with Physics with Santa and Popeye the Silent Man. We'll see you next time.